All right, so I've promised you guys a video that has taken me a really long time to make. I made a video 2 years ago called the 3 pillars of service checker analysis, right? The 3 pillars are suction superheat, discharge superheat, and system subcooling. And I haven't updated that video since I created it all those years ago. Actually, it's probably more than 2 years ago, maybe 3 years ago now. So what I wanted to do is I wanted to step it up some, not just step it up, but take it to the next level. So what I want to show you here is the live animation tool that we have here in front of us of actually a VRV3 system in 100% cooling, but also walk you through using these 3 pillars to diagnose any refrigeration issue. Now, this isn't specific to VRF. This is regular residential air conditioning, right? Split systems. This is rack refrigeration. This has anything to do with the refrigeration cycle. That means if you're taking a piece of refrigerant, right, and you're turning it to a liquid and then turning it to a vapor and then back to a liquid again and using a compressor, this is for you. But specifically, I want to talk about VRF and the 3 pillars, right? So I drew this diagram here, which is basically a triangle, right? Because that is the 3 pillars. They're all connected to each other. You have suction superheat here at the top. The reason I put suction superheat here at the top is because it's usually the first thing that I check when looking at a system. From suction superheat, we go down through our compressor, out the other side, and we get discharge superheat. From discharge superheat, we then move across here through our heat exchanger, whether it's indoor or outdoor, and out the other side, I get system subcooling. Then from system subcooling, we're going to jog back up to the top of the triangle. We're going to go through our electronic expansion valve, our metering device, and on the other side, go from a liquid down to a saturated liquid in a low pressure state. And from here across our heat exchanger again, we get suction superheat. This is how they are connected. Know it, live it, breathe it. Suction superheat to discharge superheat to system subcooling to back to suction superheat. It's this never-ending repetitive cycle. And when you look at it here on this board here, right, we leave here the top of our compressors, we go out, right, we go through our heat exchangers, we come out as a liquid, that liquid goes to the indoor units, we get our suction superheat as we come back, and we go back to our compressors, and then discharge superheat, system subcooling, and so on and so forth, and back and forth, and back and forth, and back and forth, and it never ends. This is, again, when we talk about troubleshooting VRF systems, you have to understand the connection between all 3 of these and where they fit into the system. Now, I drew you a triangle because triangle is nature's strongest shape that we find out in the real world. And here, we use this as our troubleshooting tree. Right? Now, you can get rid of all the other stuff in between and just plot suction superheat, discharge superheat, and system subcooling. But the reason I added all the components on this triangle, this troubleshooting triangle, is because this allows us to fill in the information that we may have connecting these 3 together. Remember, you need these 3 numbers in these 3 corners to form a solid diagnosis. And again, it's not just these numbers that pinpoint an exact location of where the problem is, but it lets you understand what the system looks like over time. Not just over time, but also once I plot these numbers in these 3 corners, it allows me to understand, hey, between here and here, right, maybe there's a restriction. What is the expansion valve doing? Well, it's at 2,000 pulses, but there's no temperature change across it. Well, then my issue is between these 2 numbers here. This is more in depth than what I showed you last time. Last time I showed you numbers, we talked about if your discharge superheat is this, right, 70. Okay, well, that's not crazy high. It's still within range, but it is fairly high. And my suction superheat is 30, which is somewhat in range, but also on the high end as well. And my system subcooling is 0. That tells me that my system might be slightly low on charge, right? I have a high discharge superheat, right, 70. Now, not crazy high, it's within range, but if it stays in that high range, it's an issue, right? Because we know, leaving our compressors, right, we can measure our discharge superheat. How? We take our temperature of our discharge line and we subtract it from our saturation temperature. That's how we get to discharge superheat. Elevated discharge superheat tells me that it doesn't get enough vapor, which is, again, why we start with suction superheat. We start with suction superheat because it's telling us how much vapor am I getting back to my compressor? What is the quality of vapor getting back to my compressor? Because once I know what the quality is coming into my compressor, then I can measure my discharge superheat in the next corner and determine between entering my compressor and leaving my compressor, how healthy is my compressor? If it's getting enough refrigerant, but my discharge superheat is still high, that tells me that there's probably not enough oil within that compressor, or that it's an unlubricated operation within that compressor. And again, no oil, or there's damage internal to that compressor because there is modes of operation while it's running that are showing no oil returning back to the compressor. and it's wearing the compressor out. And of course, now it always has an elevated level of discharge superheat. Maybe not all the time, but there are periods where it is unlubricated. Those are things that we can measure as technicians. Now, you don't need a fancy graph like this on a giant 86-inch screen TV. What you need to understand is, as long as you can plot these points in these three corners, you can start connecting the dots as to what they look like in between each one of these. Now again, this is a troubleshooting triangle, right? That means that you have to plot the relevant information in the corners before you connect anything else in between to figure out what your system is doing. Let's get into it. So if I look at this here, right, and let's start annotating. Now we have a system, and it's in cooling mode. What we know about cooling mode is that my outdoor units, right, they're taking hot gas and they're turning it to a liquid. So let's start where we always start, with our suction superheat at the top here. So my suction superheat is what? It's two things. It is my saturated temperature right here on my saturated temperature sensor. Let's say my saturated temperature is 32 degrees, right? That's pretty low. What is my actual suction line coming back to my compressor? Well, let's say that it is 62 degrees. Well, I know that because my saturation temperature is 32 and my line temp is 62, that I have a suction superheat of, you guessed it, 30 degrees. Well, we just mentioned that. Okay, so we know what the quality of vapor is coming back to my compressor. Now, what if I come back in here and I say, well, you know what? Let's say that this is 33 degrees on my suction temp, because it happens. Well, then that means that instead of having 30 degrees here, we have 1 degree of suction superheat. Well, what do we know about 1 degree of suction superheat? The closer we get to saturation of 32 degrees, remember this is a pressure sensor that is determining at this pressure what the actual saturation temperature is, I know that I'm 1 degree above saturation. Well, being 1 degree above saturation means I am 1 degree from becoming 100% liquid. Now, you're going to say, well, 1 degree is still superheat. And it is superheated. But how much of that is vapor and how much of that is liquid? Is it a mixture? Is it a slurry? And the answer is yes, it is. The closer we get to saturation, the higher the concentration gets of liquid within that suction line, right? Within that vapor line, because that's what it is. It's supposed to be 100% vapor in that line at all times. The way we measure that quality of vapor, quality is two things. We're measuring the quantity of vapor. If we have a high suction superheat, if I have a 60 or maybe let's say 100 degree suction superheat, then that means my superheat is way up here, which means that my vapor, there isn't any, right? So the quantity is not there. Now the quality might be there. It is 100% vapor. We know that because it's 100 degrees above saturation. However, because it is 100, that tells me that there's not enough of it. We know that when the right amount of vapor is flowing through that line to my compressor, that it's in a specific range, usually around 5 to 32 degrees based upon the mode of operation. I like to see it between 5 and 14. Now, VRF is a little bit different than other air conditioning systems. You're going to find manufacturers for residential equipment where they'll say that 15 degrees is great, or 20 degrees is great, or 25 degrees is great. The difference is this beautiful thing right here. It's the compressor. Every compressor is manufactured to handle a different type of suction superheat. Every compressor has a different health range for discharge superheat. So you can't just take the numbers that I'm showing you here and apply them anywhere. However, the concept is universal. Understanding what vapor pump I have and what it's designed to do is the whole premise of this conversation in the first place. So let's go back to 1 degree suction saturation, right? Suction superheat, 1 degree. Okay, we got 1 degree at the top. That tells me that I've got liquid coming back to my compressor. I'll even put a nice little 1 here at the top of my chart. Now I'm going into my compressor. What's going to come out the other side? Well, coming out the other side, we have what? We have a high pressure sensor. What does that high pressure sensor tell us? Well, that high pressure sensor tells us that the saturation temperature for my liquid line or my discharge line, again, these lines are connected, liquid and discharge. There is a pressure differential between there, so you may see a few PSIs fall off from when you measure at your actual suction, your liquid connection and your discharge pressure. But for here, we're at 100 degrees of saturation. That means that the pressure here of 410A, right, because this is the refrigerant the system's operating with, the RV3 heat recovery, this 100 degree saturation temperature is telling me what the pressure, so pressure to saturation temperature for 410A. So my pressure is telling me it's 100 degrees saturation. Why do I need to know that? Well, because my line coming off this unit is, let's say, 200 degrees. Well, I take my saturation temperature and I do the math, and that math would be DSH equals what? 100. There we go. Yes. That's a high discharge superheat. I know that my normal range for discharge superheat is anywhere between 32 degrees and 72 degrees. Now, every compressor is going to be different. Everybody likes a different number, and I get it, right? Why do we have a range? Why is there from here to here, right? The reason there's a range is because this is what we call an inverter compressor. Inverter compressors are designed to what? Modulate speeds. They're designed to go up and they're designed to go down. And based upon how many of these indoor units are actually calling for liquid refrigerant, or maybe liquid refrigerant and also hot gas, if they're heating and cooling at the same time, that number is going to change. So what I like to see is I like to see a nice level, even out number within an hour, 2 hours, no drastic changes in the system. Those are the numbers that I'm looking for. And so 1 suction superheat, 100 discharge superheat. Now, could this actually happen? And I have actually seen this. Why would this happen? Whoa. You're telling me right now that if my suction superheat is 1 degree and I've got close to liquid coming back to my compressor, and yet my discharge superheat is 100 degrees, how does that make any sense? Well, so here's the thing about vapor pumps. When they get liquid in them, one, it's bad. The scroll plates will actually disintegrate if they get a large enough liquid in them, or if they have a flooded start. But with this, we know we're getting way too much refrigerant back to my compressor. So my discharge superheat should be in the toilet. It should be 5 degrees. It should be 10 degrees. It should be anything below 32, right? Because again, we're compressing liquid. We're getting a mixture of liquid back to the compressor. And it's a vapor compressor. It's not designed to compress any mixture of liquid of any amount. Why would it be at 100 discharge superheat? Well, so here's the thing about compressors that chew on liquid for extended periods of time. 1, they lose a large amount of oil, but then 2, the lack of oil within the compressor wears out the bearings at both the top of the compressor and the bottom of the compressor in 3 different key places. So what happens when we lose that oil and you get 2 scroll plates that are grinding away on top of each other? Well, 1, you lose the oil that seals the compression process in between, so you get some leak by, but 2, you get an insane amount of heat. You get an insane amount of friction. Friction causes heat. Have you ever seen brakes on a car that are not properly maintained, and you slam on the brakes of your car? If you actually go check the temperature of that rotor pad, how hot is it? It's extremely hot, because that is friction. That's exactly what we're doing here. Now, these aren't brakes on a car. These are scroll plates, cast iron scroll plates, spinning together, modulating together, creating what we have here, which is a problem. And so why would I get these numbers? Well, 1 degree suction superheat and 100 degree discharge superheat tells me there's damage to the compressor, there's no oil in the compressor. And what else am I going to look for here? I am going to look for, on my compressor, I'm going to look for what? I'm going to look for elevated amps, right? Amp draw, right? There's going to be an excessive amount of load. When there's excessive friction and actual plates rubbing against each other, metal on metal, and that friction that's being created, there's also going to be a higher load on that rotor, on that stator within that compressor, and it's going to result in higher elevated amp draws. This compressor is close to pulling nameplate amps. This compressor is close to pulling amps to shut the system down. It's probably an overcurrent step down right now. Because again, I know that I'm getting liquid back, which is a bad thing, but then 2, my discharge superheat is through the roof. The difference? Lack of oil. Okay, so let's mix this up. Let's get rid of our 200 degree discharge temperature, and let's go with something maybe a little bit more reasonable, and let's do 180 degrees. You see 180 degree discharge lines all the time on VRF systems. So what does that put me at now? Well, that puts me at a discharge superheat of 80. And let's change our suction superheat back to where we were before, and that was 62. With being at 62, we're going back to the beautiful number of 30 degree suction superheat, which is more realistic on what you're going to see in your average system. So we know we have elevated levels of suction superheat, 30 degrees. We have an elevated level of discharge superheat, 80 degrees. Both of these things tell me that I'm not getting enough vapor to my pump. And then out the other side, I am also showing signs that I am not getting enough vapor, or both, lack of vapor and a little bit of lack of oil. Again, if it was a lot of oil, those are those compressors that you see turn on and then they go discharge temps 300 degrees in a matter of 5 minutes, right? And we've all seen it. So now that we've got our suction superheat and our discharge superheat, what's going to happen next? Well, that hot gas is going to come up here and it's going to go through our heat exchanger and it's going to do what? It's going to turn into a liquid, right? And then we have a choice. And the choice is, are we going to measure suction? We measure suction superheat. We measure discharge superheat. Do we know where to measure system subcooling? Where do we measure system subcooling? That's the question I'm asking you. Because when you look at this liquid line on this VRV3 system, you're going to notice that we have a few sensors. We've got one here, we've got one here, we've got one here, and we've got one here. So I've got 4 sensors to choose from. Which one do I use? So when we talk about VRF, we have something that's called a subcooler. That subcooler is vapor on demand, right? We're taking vapor, we're taking a saturated liquid, putting it into a low pressure state, we're boiling it off into a vapor, and then that vapor comes back around, and where does it go? It injects back into our suction line, back over to our compressor. It is vapor on demand. Now, its byproduct is subcooled liquid refrigerant, because again, there has to be a medium on the opposite side to transfer heat to, but its main purpose, again, is maintaining vapor to our pumps, our vapor pumps, especially when changes are taking place within the system. So with knowing that there's a subcooler here and it's influencing the liquid line and it's lowering my subcool number, that tells me that I probably shouldn't measure subcooling after my subcooler. I should measure subcooling before my subcooler. And there's a few ways to do this. Now with VRV3, we're very spoiled because there's only one heat exchanger outside, not 2, 3, or 4 on some of these larger modules. When we have Emirion systems, when we have VRV4, X, 5, give it a number, give it a letter, you know what I'm talking about. And so for here, we have a few choices. We can either measure here, right, that sensor there, or we can measure right before the expansion valve leaving our heat exchanger. Now me, personal preference, I like to measure it right as it's leaving the heat exchanger. Why would I do that? Well, I want to do that because I want a true accurate measurement, one, before and also after. Why are there 2 sensors here? Well, those 2 sensors, one is a de-icer, and the other one, which is de-icer is used for defrost, only defrost, and the other one is my actual liquid temperature for my heat exchanger. This sensor is also used for measuring superheat across this coil in the heating mode. Because again, I'm catching it before this refrigerant strainer and I'm catching it before this expansion valve. So if there's issues with this expansion valve or there's issues with materials clogged up in that actual strainer, I'm not going to get a good temperature. I might have a temperature drop. Maybe it goes from 90 degrees from here and on this other side here, it's 70 degrees. Well, that's a big issue. There should not be a 20-degree drop between here and here in such a small area. That's a red flag. But that's not what we're here to talk about. We're here to talk about system subcooling. And so with system subcooling, I'm going to look at this and I'm going to say, okay, I know where I want to measure it. I want to measure it at the change of state. Well, what state change is taking place here? We have hot gas that's going into a heat exchanger, and then out the other side, it's turning it to what? It's turning it to a liquid. It's rejecting heat to outside. And in the process of doing that, we are creating our subcooling. So again, we're going to come back here. We're going to say, okay, we have a 100-degree, right, liquid saturation temperature or discharge saturation temperature, whatever you want to call it. They call it condensing temp, right, or TC, which is condensing temp spelled backwards. And so for here, we're going to see that, okay, well, what do we have here? Well, we have a 99-degree liquid temp. And what does that tell me, 99-degree liquid temp? Well, I take 99 minus my 100-degree saturation temperature, and what do I get? I get a beautiful number 1. Now, when I say system subcooling, I am not saying that for some reason you can take your cowboy hat and hang it up on this diagnosis and you're done. Charge the customer and tell them that their system's undercharged. No, it doesn't work like that. This troubleshooting triangle is designed to help you pinpoint where the problems are. When will I hang my hat up on this? Well, where am I going to go next? Well, I built the 4 corners of my triangle. I've got a 30 up here, I've got an 80 over here, and I've got a 1 over here. Now, all 3 of these things point to what? A lack of charge, a lack of refrigerant flowing through the system. What am I missing here? Well, I'm missing, let me see here. What am I missing? Oh, I'm missing compressor speeds. What is my compressor speeds? Well, let's say my compressor speeds are at 40 RPS. Okay, let's keep moving our way around the triangle. What about my outdoor heat exchanger? My outdoor heat exchanger is at 480 pulses. It's wide open. Okay, so it's not metering refrigerant. It's not metering subcooling. You'll find on larger, newer VRF systems where they have the ability to actually meter the flow of liquid refrigerant from the outdoor heat exchanger and cooling to modulate the subcooling number. Yes, that's correct, based upon the load. So it's going to try to maintain a specific number, and that pulses amount, whether it's low or it's high, is going to tell me where it falls in that charge range. You'll find with newer pieces of equipment, they usually around half pulses to maintain that 9 to 11 degree subcooling amount that you'll see on the outdoor heat exchanger. On older models like this, it's going to be wide open because we don't do that. It doesn't have the programming for that. Let's keep moving. So where are we going to go next? Well, we're going to go to EEV. Well, unfortunately, with VRF, this triangle, it gets a little bit messy. And the messiness is that there isn't just one electronic expansion valve. Let's say there is 4 indoor units. Doesn't look like a triangle much anymore, does it? So with this, I'm going to go through and I'm going to plot all my indoor expansion valves. Well, what are my indoor expansion valves at? Well, this one's at 1900 pulses. This one's at 2000 pulses. This one's at 2000 pulses. And this one's at 800 pulses. Well, that's not good. Remember, the whole purpose of an electronic expansion valve is to do one thing and one thing only, and that is to meter refrigerant. Well, if it's not metering refrigerant, well, how do you, whoa. How do you know that it's not metering refrigerant, Roman? Well, I know it's not metering refrigerant because, again, all my indoor valve pulses are what? They're wide open. Well, if they're wide open, and now they're not all wide open, this one's at 800. And it's like, well, wait a minute, this is a small tonnage unit. Maybe this is a half-ton unit in a closet somewhere. Well, yeah, it's at 800 pulses. It doesn't need that much refrigerant. However, when we get to the larger tonnage systems that require a large capacity, right, they're at 2000 pulses, which means that they're not metering refrigerant because they're not getting enough refrigerant. We can take this even a step further because I love adding numbers to this chart, making it even more confusing for you watching. We can do before and afters, right? So I've got my expansion valves here on my triangle, and I can start adding things like, okay, so we know that on this side, right, we know where our liquid temp is coming in, and so this is our indoor heat exchanger on the top of the triangle. I can say, let's say here, this is 37, 37, 38, right? Okay, and then this one here, let's say 34. This is my, right, low pressure saturated vapor after my expansion valve, right? And it's pretty cold. Well, of course it's cold because when we look over here, we have a 32 degree saturation temperature. Leaving your expansion valve, what is it? It's in a low pressure state, right? So of course it's going to be close to saturation temperature. That's what it's supposed to be. Because remember, it's a liquid slurry. And so it's changing states. So in the process of changing states, now we're going to go through our heat exchanger, and what does it look like on the other side? Well, on the other side, when I come back over and reconnect all these dots, I find that I'm 80 degrees, 90 degrees, I'm 75 degrees, I'm 82 degrees, right? That is a huge superheat across my indoor units. Well, again, it's not metering refrigerant because the valves are wide open, and my superheat across all my indoor coils is trash. It's garbage, right? Coming in and going out. And again, what does that look like? So over here, we marked it, right? 34 degrees. Out the other side, it's 82 degrees. Coming into my valve, it's 37 degrees. Coming out is 78 degrees. Over here is 37 degrees. Coming out is 92 degrees. Well, that is a really hot space. Again, your suction temp is going to be matched by your ambient in that space. So maybe it is really hot in that room. And then last but not least, 34. And then coming out the other side, let's say this is 82. Now again, this valve is going to open up more because it's not getting enough refrigerant. Indoor units are looking for a what? 9 degree superheat across them. So again, if I'm not metering refrigerant and it's saying, give me everything you've got, and I'm not hitting my 9 degree superheat, well, this tells me that I'm not getting enough liquid to my valves. I'm not getting enough liquid to my valves. And I already knew that because I have a 1 degree subcooling on the system. 1 degree subcooling doesn't go very far with 4 indoor units. This is getting messy, but you can see how we're unpacking this problem slowly but surely. And then coming back to my compressor, we already know we have a 30 degree superheat, suction superheat on my actual line. Remember, your suction superheat is all of these superheats right here combined together On what? On your suction line back to your unit. They come together and they reconnect back to your unit. They go all to one line right here. So your suction superheat is basically your combined superheat for all your indoor units. That's still going to tell you your quality of vapor coming back to my compressor. Well, we know we don't have, let's take a step back. We know we have a high suction superheat. We know we have an elevated discharge superheat. And we know we have a crappy subcooling. Well, why doesn't the system just ramp up to maintain temperature on the indoor units? The indoor units need more liquid refrigerant. Why can't they just go and get it? Well, the reason they can't go and get it is because it's running at 48 RPS. Why isn't it running full speed? Because you have to remember that on this chart is a saturation temperature. What is that saturation temperature? It's 32 degrees. So this line is 32 degrees. Well, where's my suction pressure at? Well, my target is 32, and guess what? My actual TE is 32. So my compressor is not going to ramp up because it's hit its target. If it's hit its target and this is what it looks like, the system is low on charge, right? And this is one example out of the many that I'm going to use here as I make these videos. But this is how we troubleshoot refrigeration systems like this and the information that we have to process. Build your triangle, write down your information. This 3 numbers is just the surface, just scratching the surface of what we have to do to find the problem. Stay tuned on the next video.